find out what's called a derivative, which is instantaneous rate of change, we need limits to do it. So that's why we did all the limits. Except they squeeze in one more section, number one, before you do derivatives. Limits at infinity. You want to make sure you know how to find limits at infinity. We've already done a couple of those, right? Limits to infinity, like just, you know, like a problem where we said, what's the limit as this went towards infinity? But we got to cover everything. We got to hit every type of scenario when x is going towards infinity. So hey, a few things I'm just going to put on board just for algebraic review. This is the first thing. This comes up in my intermediate algebra class. The absolute value of x squared, or in another way, not only the absolute value of x squared, the square root of x squared. All right? I'll just leave it up here. What's the square root of x squared? X, right? Just x. The real definition is this. It's absolute value of x. And so, a lot of times, you know, we just go square root of x squared, you're right, is x. But in this particular section, we're going to really use that to our advantage. We're going to want to know the absolute value of x squared, square root of x squared, excuse me, is actually the absolute value of x, which is a piecewise function, isn't it? So I'm going to go even further. Define this without the bars. Ooh, good. It's an x or it's a negative x. Now, when is it x? If x is doing something, when is it negative x?
When x is positive.
And I'll just put an equal with one of these. Will that work? I'll put it there and I'll put it there. So there you go. So I'll just leave that up there. Just because there were a couple problems you'll notice in this section, 2.6. I can tell you which one. Number 23, number 24, have radicals in them. And that's why we're going to want that. I think you'll find it useful. I brought up the overhead because some of you remember, can't you find limits graphically? So never forget that. It's like, well, if this thing's so weird looking, it's kind of abstruse, a little difficult to understand, I will I can put it on my calculator. Maybe look at the graph. So that's why I put that there. So that's that. Is there anything else? Well, I think we should just put down one limit as x goes to infinity. How about this guy? The function 1 over x. You know what that graph looks like? Plug in a 1, what do you get? 1. Plug in a 2, what do you get? Half. Plug in a 10, you get 1/10. The numbers keep getting what? Smaller. So this graph, everyone, just kind of keeps going down and down and down and down and down, but it approaches a horizontal asymptote. Just like that. And you probably can tell. Do you know what the limit as x approaches infinity of this expression is? 0. It's going to 0. You can see it numerically or graphically. So that's why I wanted to leave that up there. We can leave that up all class. Whenever, like 1 over x, it's going to 0. By the way, this graph, there's something going on over here. I should show it. It's over here like this. So this graph, everyone, if this is the y-axis, this is the x-axis. This graph actually has a horizontal asymptote and a vertical asymptote. This thing has a horizontal asymptote at y goes to 0. It's actually got a vertical asymptote. Let's label it here. Your vertical asymptote is the equation x equals 0. But the limit as x goes towards infinity of 1 over x is 0. Just knowing that numerically or graphically really helps us out. Cool. So let's start with concentrating on rational functions. That's where I want to start today. Rational functions. And once we know how to make these graphs, then we should find it easy to make the limits. And this is just a, 5-10 minute review on how do you graph rational functions. Because if we can make the graph, then we can find a limit. Finding limits graphically is not hard if we know what the graph looks like. So there's basically 3 main scenarios with rational functions. Rational function is just a function defined as a over b, where b is not equal to 0. All right, so one example would be this. Y equal to 2 over x minus 3. And I want us to make the graph. So we're just gonna do a little graph review. We'll do 3 scenarios. So I wanna look at this graph, or when this thing has a VA and an HA. It's got a vertical asymptote, but it also has a horizontal asymptote. How do you find the vertical asymptotes of rational functions? Brilliant, he knows, that was great. They said, look, he goes, look at the denominator, set it equal to 0, you know exactly what the vertical asymptote is. Right here, I want to give you your VA. So it's at x equal to 3, right? I'm going to go over here, 1, 2, 3, just. I can use this chalk for the asymptotes. Here. Right there at 3. All right, now how do you get the HA? Well, there's a few scenarios. If it's rational, everyone, that means there's a polynomial up here and a polynomial down here. A simple way to do it is, if your higher exponent or power is in the bottom, it's 0. So what's the exponent of that 1 right there? 1. What's the exponent in the numerator? 0. It's an x to a 0. So where's the highest exponent located? In the denominator. And if your highest exponent is in the denominator, then yes, this HA is always for a rational function right there on the x-axis. So don't worry, we'll do another scenario. You go, well, what if it isn't on the bottom? But on this, it's just an easy way to make a graph, and now you got to plot a couple points. We'll get the graph going. Here, just make a little table. What would be 2 easy points to plug in? How about 4? We could get a point over here, and then what's a point on this side of 3? 0? I'm just picking 2 easy points to plug into the graph and make a sketch. Cool? All right, what's 2 over 4 minus 3? 2. All right. Everyone, I know half the graph. Very good. There's that graph. But notice it's flattening out. You and I are going to look at limits as x goes to infinity. Well, if we can see this, we know where it's going, that's going to give us our answer. Now, what's going on at 0? Negative 2/3. It's like right there, because there's the origin, everyone. Here's the y-axis, there's the origin. So it's a little bit lower than it, but this graph is on this side, is now going to, see, it curves towards these asymptotes. There it goes. Your calculator makes these 2. But hey, why is knowing these graphs so helpful in this section? Why do I start 2.6 with this? Because they're going to ask you to find the limit as x approaches infinity of something like 2 over x minus 3. Well, can you see it? It's just going to be the horizontal asymptote, what I call the horas. It's just going to be the horas, isn't it? Right? Which is just what? 0. Find your horizontal asymptote. You'll find your limit as x goes to infinity of a rational function. Right? You go, is that for all rational functions? Well, there's one scenario we got to be careful of. Is when no horizontal asymptote doesn't exist. And it has a slant asymptote. And we'll talk about that. Alright, so there's one scenario, and that's the scenario if the highest power is where? Located in denominator. So then we're like, okay, we got it. So we put a big wall. We're like, well, what if the powers are the same? So how about y equals 2x plus 3 over x minus 1? Well, where's the VA now? 1. And you and I will talk about the HA.
2.
Oh, I heard it, it's 2. How did you do that? That was good.
Yeah, because x at the numerator and denominator has the equal like number.
Exactly.
Or something.
Victor, brilliant, that was awesome. Evan, do you notice the highest power in the numerator is a 1? The highest power in the denominator is a 1, they're matching. So if you're curious, like, how do you find a horizontal asymptote? If the highest powers in each part are the same, it's the coefficient, or the ratio of the coefficients. You go, really? Always. If it's a rational function, polynomial over polynomial, like this. Absolutely. And what's so great about this? Because when you do your limit to infinity, it's the horas, right? So that's why it's so helpful to know that. this HA is y equals 2. Well, we'll make the sketch, but when we gotta find the limit as x goes to infinity, we know where it's going. Alright, so here, I just think it's good to make these graphs so we can really see it. Seeing math helps. Alright, right here, there's a vertical. And then there's a horizontal at y equals 2. So the graph is gonna flatten out there. Let's get a couple points going. Okay. How about x equals 2 and x equals 0? I do either side of the vert S. What's going on at 2? 7. What's going on at 0? -3. 2 got up to 1, 2, 3, 4, 5, 6, 7. Way up here. Well, there it is. See it? And this graph's just going to go, and then just right towards infinity. And over here, it's going to go through that point and ride towards the S horizontal asymptote of y equals 2. So this HA, here's the HA right here. Y equals 2. And there's the VA. So I'm going to write it down. What's the limit as x approaches infinity of the rational expression 2x plus 3 over x minus 1? It's just what? 2. Graphical. Our knowledge of horizontal asymptotes. In fact, check this out. What's the limit as x goes to negative? Over there. 0. It's the same, isn't it? It's the word. Same thing over here. What's the limit as x goes to a negative infinity? It's a 2. It's not negative 2. It's the same. It's also 2. They're both 2s. So let me get this a negative. Sorry. Negative infinity. As x approaches negative infinity or positive infinity, the limit of this rational expression is the rational function will be 2. So those are 2 easy ways. Please use that to your advantage when you're dealing with rational functions. But there's one other scenario. We did highest power in the bottom. We did powers are the same. What's the other one? Yeah, what if the highest power is on top? So just something like this. How about y equals x squared over x plus 1? I mean, something just as simple as that. That's a rational function. F of x equals x squared, but the highest power is on the top. Well, let's do this. VA. HA. Well, let me just get to this one. It doesn't have one. It has a slant. And when it doesn't have a horizontal asymptote, it has a slant asymptote when the highest power is on top. So now we're noticed that this process of finding the limit doesn't work so well. But there's another easy way to deal with this one, so we'll be good. All right, where's the vertical asymptote? -1. All right. It's over here. Sure.
Can we like divide the numerator by the denominator to find the slant edge?
Brilliant. You want to do it?
Yeah.
Let's do it. And I'm going to do it. I don't know if you knew this. There's a way to find this slant asymptote. We're going to go in here. I'm going to do long division. Now, if you're like going, oh gosh, that's a pain, we'll do it. But I do want to point out you don't have to do it to find the answer. All right, but I think it's a good idea so we can see what the graph would look like. So when I'm going to find this slant asymptote, you go, how do you do it? Well, we have to do something called long division. What's that? Well, we put this like this. Put this over here. And then you got to go like this. I'll hide the 1. X times what is x squared? X. Then you multiply this x to both of these and you put it right here. So you get x times x is what? X squared. X times a 1 is a x. And you subtract down. Usually by now I have students like in calc class, they're like, oh my gosh, this is a pain. You can find the limit without doing this, so we'll talk about that. Now, do I add or subtract down? Subtract. That's a 0. These cancel, but 0 minus x gives me negative x. Now you ask yourself the same question. Hide the 1. X times what is negative x? Negative 1. And when you just found the equation with slant asymptote. It's right there. I'm going to go back and finish this out. Distribute, multiply that negative 1 to both of these. You get what? Negative 1 times x? Negative 1 times a 1. But this is just a remainder. When you subtract down here, see that minus 1? This will just be a remainder. So these go out. But 0, remember there's a 0 here. 0 minus negative 1 is just, that's your remainder. It doesn't affect the slant asymptote. That number right there. So don't think you need that number. It's right here. This is the equation of your slant asymptote if you want to do it. It's right there. Y equal to x minus 1 is the slant asymptote, which is a line that does what? It went right through here and it goes, the slope is 1 and it just keeps going up by 1, right? Rise 1, run 1. Rise 1, run. It's just a straight line. But I thought it'd be good. I thought it was a great idea we did this because we can get a sense, oh, we can make the graph now. The graph's going to either be like in here, it might be over here, maybe over here. We just got to plot 2 points. So let's get 2 points. Everyone, little table? How about plug in 0? What's 0 is 0 plus 1? 0. So when I got part of this graph, it goes right to the origin. Remember it bends towards these asymptotes? Here it is. It's like a Nike swoosh. There it goes. But you know what? I know the limit. As x approaches infinity, it's shooting towards the sky, which is what? As x goes towards infinity, where's this thing going? To positive infinity. So that's why doing a graph, you can really see where the answer is. Hey, I'm going to get another point. What's the number less than negative 1? Negative 2. That's 4 over negative 2 plus 1. Negative 4. Which puts it 1, 2, 3. And when that's down in here. See that little triangle there? And when it's right in this triangle. We didn't need it for our answer, but I did want to point out this graph does exist over here. Does this? Let's see, like that. That's what we wanted. Now let me put it down. What's the limit? As x approaches infinity of x squared over x plus 1. Oh my gosh, it's going to what? Positive infinity. Now I want to talk about this. I said you don't have to find the slant aspect to find these answers, right? So can we make this one easy? If you don't want to make a slant asymptote? Here's the deal. If you get this scenario of highest power on the top for rational functions, I want you to ignore this 1 here and I just want to divide that. And I want you to think the end behavior of that function. What's x squared over x? So I'm going to write that down. Y equals x. And when this is called the end behavior, the end behavior of this expression, if I divide, you see that big? I'm just thinking, that'd be y equals x, right? Do you know about that behavior? If you know the end behavior of that, you know the answer to this question. How does that graph behave? It does what? Y equals x goes like that. So where's it going? As x goes this, that's what I mean. So you only have to do that. You can just go in there, take this, reduce it, and think about that expression as x goes to infinity. The end behavior of that expression. Isn't that cool? And it works. So I wanted to give you a few more that you can do, so you can sit there and go, all right, let me see if I can just find the end behavior of that.
What if it was like x cubed or something?
I like it. Yeah, x cubed over x. Now that makes that x squared brilliant. He goes, but now you get a parabola, but guess where it's still going?
Yeah, it's still like that.
Exactly. So I love that how you knew that. You go, wait, you're going to get an x squared now, but you knew to look at the end behavior. And there it goes towards infinity. Isn't that cool? So absolutely, you do not have to go through this. If you're just like, I don't want to do this. No. Look at, for this scenario here, higher power on the top for a rational function. Look at the end behavior of that expression. Okay? All right. This is just a whoreass. This is just a whoreass 0, right? Yeah, you're like, got it. I think we got this stuff. Okay. Pretty cool. Well then, let me throw 3 at you and see how you do. See if you can go 3 for 3. 3 for 3. Oh, is that okay? I'm racing?
Yes,
Nice. Nice. Yeah, those things have slant asymptotes. Get it out of the way. Hey Joe, I have one more, real quick. What about that? Anybody know that end behavior?
Flip,
What is that equation? If you reduce that.
right? Negative.
Y equals negative x, and how does y equal to negative x behave? What's the end behavior of that graph? Joe got it. He says it's going to negative infinity, so what would be the limit as x approaches infinity? Negative infinity. Does everyone see that? True? So I'll write down, look, the limit is x goes to infinity of a negative x squared over x plus 1. Well then, it's got to be behaved just like this to find the actual limit. Negative infinity. Hey, can you do this numerically? Remember, there's two ways to find limits. Algebraically, numerically, and graphically. I mean, can you find that numerically? Yeah, just start plugging in what? Really, 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 really big numbers, like million. What's a negative million squared over a million plus 1? See what happens. Then try a trillion. And you'll probably see it keeps getting very, very large in terms of negative numbers. So always keep that in the back of your mind too. All these tools we can use to find a limit. All right, here you go. So what we're really concentrating on right now is, you and I are like, hey, let's hit these things graphically. But even better, you're like, if it's a rational function, won't it just be the Horace? Yeah. All right, try to find this one. X minus 6, x squared, minus 3x, plus 11. The limit as x approaches infinity. 3x squared minus 5 over 2x squared plus 1. Usually I say, show all work for full credit. Right here I'm just like, you can just find the limits. Here's another one. Find the limit as x approaches infinity of x cubed minus 9 over negative 4x squared plus 5x plus 1. All right, they're all limits to infinity. This topic, limits at infinity. What's one at infinity? You could go and make the entire graph if you wanted to. On this one, highest powers in the numerator, you could go find a slant asymptote if you wanted to. But please feel free to use these tactics, these easy tools. In these two scenarios, it's going to be the horizontal asymptote, right? True? Just find the Horace, you'll get the answer. This one has a slant as, so we're going to look at the end behavior, right? Joe, do you know this one? Where's the highest exponent?
On the bottom.
On the bottom. And when the highest exponent's on the bottom, no matter what, where was the Horace every time in a rational function?
0.
Always 0. It's always 0. So guess what this is going to be?
0.
By the way, I'll show this other ways to do these problems. There are numerous ways to find these limits. There are. But this is just one easy way. You're like, it's a rational function. I know what the horizontal asymptote is. That's going to be the answer. This graph is going to head towards the horizontal asymptote. How do I know it's 0, everyone? 3x. There's no x here, there's no x here. I look for the highest exponents. There was a 1 versus a 2, higher exponent at the bottom. Now here the exponents are matching. Highest exponents in each part are matching. Where's the Horace in that scenario?
3 halves.
3 halves, good job. Or if you want to write 1.5, that'll work too. I'm doing this without any graphs because of our knowledge. This works. And again, So I can just do that, of course you can. I think it's great, because you're just applying it, you understand where the horizontal asymptotes are. Don't need to make the graphs, you're just asking for the limit. All right, do you remember a fast way to do this, where you don't have to make the graph and get the slant asymptote? I want you to think of the end behavior if you simplify it. Let me hide that 9, I'm going to hide that 5x, hide that 1. Does anybody know the end behavior of that graph? It would be a negative 1/4 x. So what's the end behavior of y equal to negative 1/4 x? That's a straight line. Which way is it going? It's going down. So what's the answer to this limit? Positive infinity or negative infinity? I do want to point out, this is either going to be an infinity or negative infinity. If you really wanted to guess on a test, it's a 50-50 chance. This will always be infinity or negative infinity, but no. Let's look at the end behavior. It's going to negative infinity, isn't it? That's what it is. So we get negative infinity. That's what you get because that 4 had a negative in front of it for the coefficient.
I have a question. How do you find the limits of the first one and the second one?
Oh, how we found these? We knew that these would be the answer because we knew these were the horizontal asymptotes. Remember we made the graph earlier and the highest exponent was on the bottom? The horizontal asymptote will always be, I'm just going to draw, not the entire graph, but just, I'm going to show you where this horizontal asymptote, it's right here. And so what will the graph do? Whether it's up here or down here, it's going to bend and curve towards that. Now in this scenario, these powers are matching. That's your horizontal asymptote. So this graph's going to do what at there's 1, there's 2, 3 has to be right in the middle, 1.5. This graph is just going to bend towards that. It's going to approach this. If it's up on top or it's down on the bottom, it's still going to approach it. In fact, actually it will approach on that side too. So that's what we're doing. And feel free to do that. Hey, was that okay with all these? Now I really should show you something. I get a lot of students, let's say they're taking my Calculus online course. I don't see this. I see a lot of algebraic work. Maybe they get it right, maybe they get it wrong. I get all these steps, so I want to show you what they've been taught. And it works. Like what would a solution manual say? I just want to show that to you, okay? What would a solution manual show for this? Can I erase these, Turk? Okay. So I want to show you this too. This is what a solution manual. So I get students who go, oh, I like that better. They don't like graphing and shortcuts, you know? They're like, oh, I'll just do this. All right. Gets us out of the way, we're looking for this limit. All right. So, when I want you to look at all these expressions in here, that's an x, that's a 6x to the 0, that's x squared, that's a 3x, that's 11. Of all those little monomials in there, what's the highest power you got? X squared? So what I'm going to do is, do you agree in math? The beauty of math, you can multiply 1 to anything. So what I'm going to do is, I'm going to go up to this expression. I'm going to multiply 1 over x squared over 1 over x squared. Okay? So I'm in this top, this numerator, I'm going to multiply 1 over x squared. And then in the denominator, I'm going to multiply 1 over x squared. All right? So this is what a solution manual would show. Now, my next step, let's see what we get. No, you don't have to do it this way. What's 1 over x squared times x? 1 over x, very good. Minus 6 over x squared. X squared times over an x squared is just the number what? 1 minus 3 over what? X, and what's that last part? Plus 11 over x squared, right? So far so good? Now this is going to be helpful to us. What's the limit of like a 1 over x going to be? It's just going to be what? 0. And we're going to use that to our advantage. By the limit laws, this would be the next step in the solution manual. They'd show this, they'd show this. Now, the limit law says you can write this limit next to that, 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 and just find all the limits and see what you get. So I'm going to do that, okay? It's going to be a lot of writing. So I mean, so watch. I'm going to write lim, x goes to infinity of the 1 over x. Minus, the limit as x goes to infinity of the 6 over x squared. Somebody might be already tired, like, we know the answer, it's just 0. Let me give you a limit as x goes to infinity of a 1 minus the limit as x goes to infinity. This is no lie, this is what the solution manual would show. Plus the limit as x goes to infinity of the 11 over the what? X squared. But I see this all the time. They've been taught that in high school. It works, they like it, and they just keep doing all this, and it's no problem. Now you gotta find all these limits. Well, what's that limit? 0. What's that limit? Do it numerically. 0. You probably already know the answer because you're getting zeros on top. That's a 1. And when you read the limits x goes to infinity of a 1 is just 1. It stays flat line 1. No matter what, it's always 1 because that's 1. What's that limit? 0. What's that limit? 0. You agree? Well, what's that mathematical answer? 0. So I want to point that out. That's another way to do these. You look for the highest. I looked for the highest power I saw, and I did a 1 over that in the numerator and denominator. It works. Just takes a lot, but I see that all the time. You might go, that's a lot of writing. Some students don't mind. They just go and they just keep writing it out. But I have seen them all write it out like 8 steps like this, and they get it wrong. They mess up just one of these, what happens? Yeah, out of 1, 2, 3, 4, 5, mess up just one. That's all it takes to throw the thing off. True? Like if they didn't see that was a 1, they put a 0 there, and I might go 0 over 0, and then think does not exist. Why do you think like that? Excellent, excellent.
You said you took the x with the highest power.
Yep, and then I did 1 over that. So if I saw like, no lie, if I saw like an x to the 5th up in here, and an x to the 6th down here, and then all these other powers that were lower, I would have done a 1 over x to the 6th over a 1 over x to the 6th.
But it'll still be 0.
And you'll still get to be 0.
I-
Yeah, you're right.
No clue how you got that, but I'll do it.
Yeah, you're right. Hey, that other one, I'm going to rewrite the one I had. What was the second one I had where the powers were the same? It came out to 3 halves. What was it? 3x squared, 2x squared. Do you remember what I had there?
Minus 5 and plus 1.
Oh, thanks. So, what's the highest power you see?
2.
If he likes it. Okay, so you would multiply up here a 1 over x squared, and then the denominator you'd multiply a what? 1 over x squared. You distribute it, you would distribute it, and do all the math, but you should get, if you want to try it, you should get the answer of 3 over 2.
So you ignore the coefficient.
That's right. Isn't that cool? That's what you're looking at. You're ignoring the coefficient. Because the beauty of math is, I'm allowed to do this, aren't I? I'm multiplying the expression 1 with the number 1. 1 over x squared over 1 over x squared is 1. Did you want me to finish that one out for you?
No, it makes sense.
Okay, he's got it. So some students like that. Like, oh, I don't like the graphs. I don't like whoreasses. You know? I like this. This is all out. They're algebraic. They're algebraic thinkers. They like the way that it works. That works even with the x cubes and stuff. Cool. All right, so are there any weird, bizarre ones? Yeah, what if it's not rational, but it's a fraction? So in this phrase I was just saying, rational, like this number in math is rational, this number is not rational. So what if it's a fraction, but it's not a rational expression? Well, I guess that game's over, huh? Well, we can still use parts of it. So I'm going to give you an example. What if you got something that's not rational and we still want to use some techniques here? Well, you can do it the way we were just doing. You can still do it. But here you go. How about x squared plus x plus 2. And you and I are going to find the limit. That's a rational, I mean that's a function, but it's not a rational function. You and I are going to find the limit as x goes to infinity of it. And then we're going to find the limit as x goes to infinity, except, I'm sorry, negative of the same expression. Believe it or not, everyone, I always like to start out with doing those little short, fast ways to do it. That's how I'm going to start this. Okay? Now, some ideas, if you got something like this, you're doing a test, and you never saw this approach prior, I mean, couldn't you really put this into a calculator graph and see what's going on? You surely could. Investigate it. Let me just see what goes on with this graph. So that's something we might consider. I might pop it up there in the end. But I guess it's not a rational function because it has a radical, true? But we can still approach it the same way. Like, what's the highest power up here? X to the first. If you think about these as separate, the highest power in the denominator is right there, x squared, but it's got a what? Square root. So, and Joe, you told me earlier, square root of x squared was just a what? Just x, right? So think about it, when you've got a 2x with a what? An x. The only thing we got to be careful of is this. Because it was the square root of x squared, which is technically a what?
Plus minus.
Yeah, a plus or minus x. So, what we're saying here, everyone, if you're going towards positive infinity, which one of these two would it be? That piece or that piece in the top one? If you're going towards positive infinity.
X.
Yeah, so I can actually think of this as an x. But what about this one as you go towards negative infinity? Then you're going to have to think of that as the what?
Negative x.
Negative x. Now we're going to be able to get these answers in a very short, easy way like before. I'm looking at this. See all this right here? I'm thinking of that as, aha! That's like a 2x over a positive x, which is just a what? So guess where the horas is. This thing has a horizontal asymptote. There's a horizontal asymptote at y equal to 2. Guess what the limit is? That's the horizontal. It does. It's a funny looking graph. That's why I was going to fill out the graph in calculus. See how nice it comes out in the calculator. This graph has a horizontal asymptote at y equal to 2. So what's the limit going to be? It's like, I'll just do this. It is just going to approach that 2. You betcha. You betcha. You really? I didn't have to make the graph. I know that because of this portion right here. I took up the highest piece.
What if it was 2x squared and x?
2x squared over x. Any radicals in here? Oh, then you're back to the rational functions. Right? Do you agree? If you just had this, but you don't have any square roots, then you can think of this as higher power on the top. Think of the end behavior, it's going that way. That's going towards infinity. Do you agree? Even if you had this here. Look, now you got a rational function. Do you agree? Look, end behavior. 2x over x. What's the end behavior? That thing's simplified. It's going to infinity. The limit as this goes towards infinity. Hey, and when this thing has a positive, but what about this right here? There it is. But this is going towards what?
Negative.
And now look, we're coming back to this definition. We know that the absolute value of x is actually two pieces. And when x is less than 0, it turns into what? Negative x. So how am I going to think of this part now? Because of this.
2x over negative x.
There you go. Good job. This is my, what I'm going to call it, my horas. It really does. This is the horizontal asymptote right here. There's a horizontal asymptote of this function, this funny looking function with the radicals at y equal to 2x over negative x. This had a horizontal asymptote at y equal to 2. I'm going to write it this way, 2x over positive x, which is 2. This is just a negative what? So what's this answer? Without any graph, without any algebraic work, this has to be 2. What's this answer? Cool. Now I think we should take a second and definitely check it. If you want to go and do it that way I did before, go right ahead. What do you think you would divide everywhere? I would divide x squared, because even though it was in a radical, what was the highest power?
Okay.
I would divide x, 1 over x squared, good. 1 over x squared there and 1 over x squared there. But then you gotta insert your 1 over x squareds inside the that radical and stuff like that. Alright. Hey, when I'm gonna hit the light here. Let's look at this thing. What was the equation? How nice is this? Is it nice? Oh, I gotta turn my plot off. Zoom 6, right? For a nice window. And y equals, what did it have? 2x divided by square root x squared plus x plus 2. How good is it? Oh yeah. And when you want to use trace, I'm going to trace this baby. Watch the y value. Just watch. Where's it going? can zoom this better too. We really want to see these numbers a little bit better. That looks better. I'm just keep hitting trace, okay? Go, right arrow. Where does it look like that's going?
Closer to
It's getting closer and closer and closer and closer. There's a horizontal asymptote right there. What about over here though? What's going on when you go towards negative infinity? It's going towards what? Negative 2. Cool. So that's what that graph is. So this is a great tool just to investigate things like this. Like, are you sure? That looks complicated. You should pull this out and go look at it. So please feel free to do that. Please feel free to do that. Isn't that cool? All right. Yeah. Hey, well, let me look at the craziest one out of this section. I want to look in front of the radical. Will you try it? This is number 24. The page 141. Find a limit as x approaches negative infinity of the square root of 9x to the 6 minus x all over x cubed plus 1. This is going towards what? Negative infinity. So when I want you to see, everyone see that square root? Don't forget it. This, right? Okay, let's see the behavior of all that. Is that a square root of 9x to the 6? What would that be?
Wouldn't that just be 9, x?
Square root of 9 is 3, right?
Yeah.
Good. And then what's the square root of x to the 6?
X to the third.
Third.
X to the 3rd. But is it positive or is it negative? Because this is going towards negative 9. And it's x cubed, isn't it? Hey, what'd you put, x squared?
I kept the 9. I didn't take the, I thought it was going to be the 6 with a.
Oh, I gotcha.
3.
So that's the top thing right there, right, everyone? Why did I make it negative though? Go there. Now what's this bottom half right there? This should be our HA. This graph has a horizontal asymptote at y equal to negative 3x cubed over x cubed. Do you know the answer? Without even making a graph,
-3.
y equals negative 3. The limit? Negative 3. You bet. Because it was going towards negative 3. Hey, that seems like the craziest one. They have one with e to the x's and e to the negative x's. You just gotta have knowledge of those graphs. E to the x exponentially grows, e to a negative x exponentially decreases and goes towards 0. Cool. I'm sure you'll get 15's great practice, 17's great practice. 19, it had a square root in it, but it still didn't have the highest power. The highest power of t squareds. Cool. Hey, please keep in mind, I even would spend more and more time on this section. I would. But there are other great techniques to go on limits to infinity. Has anybody had calculus before? Oh, there's always one. All right. Do you remember L'Hopital's rule? L'Hopital's rule?
I remember.
Okay,
learned it
L'Hopital.
at the end of the year.
All right, now L'Hopital's rule deals with limits to infinity. It's a very, very, very elegant way to find limits. We just got to learn about derivatives first. So I can't teach it now because we don't know derivatives. But once you get derivatives down, there's another way to what? Deal with these. And what I find, this is what I point is, I look on final exams, what techniques students do, and I see students use that more often than this stuff. You know, it's good to know about horizontal aspects. When it gets a little more complicated, they're using like, maybe perhaps L'Hopital's rule or something like that. Keep in mind, hey, to summary this, what's the 3 ways you can find limits? You can do it what? Graphically? What's the other way you can find a limit? You can do it numerically. You just plug numbers really close to it. If it's going towards infinity, you put very, very large negative numbers. Very, very large if it's going toward positive. And then the last way is you get these two-side limits, and we're just doing it algebraically. And this problem algebraically would be multiplying like, well, whatever x to the 6th, whatever x to the 6th. Cool. Alright, good deal. Alright, oh cool, we get to define a derivative. Derivative of a function. Alright. What is the derivative of a function? We won't need this anymore then. We don't need any of this, that was just for limits. Alright, derivative of a function. Derivative of a function. Let's define it. There's a point. Here's a point. And there's our function f of x. Let's label this as x. If I call that x, anybody know what I can call the y value at x? F of x. Will that work? Yeah, okay. Alright, cool. So far so good, I'll get this out of the way. We're going to define a derivative. Now, we're going to use that letter h. I saw h in that last section. So when I do a distance from this point to this point, horizontally, I'm going to call this h. From there to there, this horizontal distance, from this location to that location where that is, that horizontal distance I'm going to call h. H for horizontal, all right. So, I want to see my dot right there? What do you think I can call that value then? That'll work. X plus x is the distance from there to there. The distance from here to here is h, so I can call this x plus h. Sound good? Remember, we're doing this as proof, so we're going to actually derive this, come up with some expression for the actual derivative. So that's x plus h. Now, I said, what's the y value at this x value? We called it f of x. What do you think you call the y value at that x? F of whatever that is, right? What's the y value here? F of x plus h. That's what I call it. Alright, so that's f of x plus h, that's f of x. Now I'm going to start out, before we do a derivative or a rate of change, let's just go back to college algebra. Not pre-algebra, college algebra, algebra 2, that kind of stuff. And if I took a straight line from here to here, that's called a secant. So I just want to let everyone know this is called a secant. It's a segment that actually went and intersected this curve in two places. Cut through the curve, it's called a secant. What's the math formula? Just go back to algebra days. What's the algebra formula for slope of a secant? We need to start there before we get the formula for the derivative. Because it deals with slope. What's the slope of that secant? Y sub 2 minus what? Y sub 2 minus y sub 1 over x sub 2 minus x 1. True? Alright, but help me out. What's this y sub 2? What's this y sub 1? What's this x sub 2? What's that x sub 1? Maybe we should write them as xy coordinates. That point right there, one is the point. X plus h, comma, x. What's this point? That point right there is the point. X, comma, f of x. Right, everyone? So what would this come out to be? That's x, comma, f of x. That's x plus h, comma, whoops, what's this? I apologize. This is f of what?
X plus h.
Yeah, I saw the eyes. Like, what'd you write up there? X plus h, comma, f of x plus h, x, comma, f of x. All right, let's jam it all in here. And when y sub 2 minus y sub 1, okay, slope is secant, y sub 2 minus y sub 1, f of x plus h minus f of x. Now how about the x's? X plus h minus x. This is the math formula for slope of any secant. If we're dealing with this funny little h in there. Now, can I simplify anything in there? What does that come out to be? Remember, this is just the theory. If you hate theory, you can ignore all this and wait for the formula. This is kind of fun. What simplifies in the denominator, though?
It's h.
Yeah, it's just h. So this is actually the formula, I guess, in terms of any function where I reference as h the distance from this point to the next point, in terms of a horizontal distance. That's slope of a what? Secant. I want to tell you what we're trying to do in section 2.7. You and I are trying to come up with a formula for the slope of a tangent. All right? This is slope of a what? Secant. You and I got to figure out a elegant math formula with math notation that represents not that slope, but what color is this? Pink or red? I'm not sure what color.
Kind of salmon.
Okay, thank you. We're looking for this slope. Right there. We need a formula for that. We need a formula for that slope. We know the formula for this secant, right? So here's an idea. How about we just draw another secant, but we'll bring it closer. Remember when we kept getting closer and closer and closer? So everyone, this is what I'm going to do. You ready? I'm just going to keep erasing. I got it easy because I'm going to keep erasing. But remember, we're just doing the theory here. So there's slope of secant. True? I'm going to move this dot now. I'm going to bring that dot closer. How about right here? Right there. Ooh, look at this. Now when there's x plus h, and there's my secant. Am I getting better towards that salmon tangent? Am I getting better? It was over here, but now it's getting closer, isn't it? What did I do in terms of this h distance? My h distance what? Shrunk. It got smaller, right? Can I improve this? Yeah, make another secant, but what? Get even tighter. So I'm going to do that again. Here I go. Take it off. Take it off. Get closer. Get closer. Get tight. Get up in here. How about from here to here? Ding, ding. Still a secant, but oh, I am almost like the salmon, right? And right next to it is this x plus h, where the distance for h is just this tiny what? Distance. So everyone think you can do it? Can you come up with a formula for the slope of a tangent to the curve f of x at the point x? Can you do it? It has something to do with this. I just gotta put something in front of this. Limit. The limit as h approaches what? Help me out. What was I doing with that h distance? The limit as h approaches, what was h approaching? It kept getting smaller and smaller. H was like there, then it was here, then it was there. The limit as h approaches 0. You agree? Remember how h was? Let me go back to the original. H was like this far before. It was way, look at the distance for h. Then I took it tighter and h went from like here to here. It was about there. Then I took it tighter. H went from there to there. Then I took it tighter. So what was going on this h distance? I kept taking it until it was what? 0. It's a limit. So right in front of this, all we have to do is write what? I mean, how cool is calculus? Now that we know limits, we can apply it. I'm serious, like in defining something in a very elegant way with notation. That is how we define slope of a tangent to a curve f of x. But you need a limit. The limit as h approaches 0 of this expression. And now, boy, you can now find so many cool things. Because, what if f was position? This is a formula for instantaneous rate of change. Isn't that cool? So this is pretty powerful. What we're saying, this is very powerful. Number one, it finds slope of a tangent to a curve at a point. Number two, this finds if your function's dealing with position, this will find the instantaneous rate of change of position, which is instantaneous velocity. Alright? So and I'm going to take this whole secant thing out of the way. By the way, do you remember what slope of secant is? That's not instantaneous rate of change. This was average what? Average rate of change of a function. Do you remember that? Then what's this? Slope of tangent. What's this in terms of rate of change? This is instantaneous instantaneous. Want to make sure I spelled it right. Instantaneous rate of change of a function f of x at some point x. Isn't that cool? You just jam that in front and you're getting what? Instantaneous rate of change. Cool. And I mean, this is a lot of wording, isn't it? Look, slope of a tangent to a curve. What else do I call it? The instantaneous rate of change of f of x. So in calculus, we just want one word to make this simple. Guess what they call this? They call this a derivative. The derivative of what? The derivative of f of x. The derivative of the function. Make it short and sweet. Come up with something. They call it the derivative of the function. So when that is the derivative of the function. You saw this word derivative here. What is the derivative of x? All this. This right here. This is the derivative of f of x. By the way, you can define it some other ways. I like to do it with the h go to 0. Now, you know in math that when they invent all these funny symbols and stuff, now they got to invent a symbol for this. Right? They need to invent a symbol to represent this. Right? That's not going to cut it because that's f of x. So they actually made a good call here. Are you ready? They made a really good call. They said, just write f of x again, but just do something to your f of x. Guess what they put right here? They just put a little prime slash like that. So when you see that? That's the symbol. That's the note. It's not the only notation. This is the notation for first derivative of f of x. And you can call it f prime of x. In fact, you can just write it like this, f prime. Just put an f, a little dash there, f prime. Is there another way to do this? Yeah, you can call it dy dx. You could write it like that. This is another notation. This is, I'm going to read it as a sentence. The derivative of the expression y with respect to x. I think it's good that you know that. That's how you communicate this. The derivative of y with respect to x. You go, why? Because what if we do like the derivative position with respect to time? You know, we might be able to think, oh, that's velocity. Cool. So derivative of y with respect to x, dy dx. dy dx, f prime of x. These are all different ways to what? Write the derivative function. What is it? It's this. Cool. What's this without the limit? This is just what kind of rate of change? Average rate of change. Cool. All right, hey, let's do a problem. Let's do a problem. Can I pull this thing off? Yeah, I'm going to take this off, and right next to this, I'm going to write this. Lim, h, arrow 0, f of x plus h, minus f of x, all over h. This is equal to what symbol? F prime of x, right? What's this called? The derivative of f of x, right? What does this find? This finds slope of a what? Of a tangent to a what? To a curve, f of x. What else does it find in terms of rate of change? What kind of rate of change? Instantaneous. Just leave it up here all class, right on? There we go. F prime of x. Anyone read that? That's just an f prime of x. That's the symbol here. F prime of x. Does this have a symbol, average rate of change? Yeah, how about delta y or delta? Will that work? Average rate of change, yeah. Change in y over change in x. That works, right? Is that true for this? Average rate of change. Cool. This is derivative. All right. Let's try it. Go in here. Here you go. Everyone in this problem? A particle moves along a line so that its position at any time t greater than or equal to 0 is this. Alright, a particle moves along a line So that its position at any time t greater than or equal to 0, so time has to be positive at any time t greater than or equal to 0, is given by, well, you know in physics and calculus, a lot of times they like to use the letter s for position. So position of particle, that's an s, not a 5. S of t. S of t equals t squared minus 5t plus 2. Actually, I apologize. I want to make that a 4. Sorry about that. Negative t squared minus 4t plus 2. Okay. Letter A. And when I want you to find the average velocity. So if I say average velocity, and don't you agree I have to give you 2 points at a time? Find the average velocity, well, between what 2 times, okay? So find the average velocity, all right, during the period t equals 4 to t equals 7. Find the average velocity during the period t equals 4 to t equals 7. Do I need the derivative formula? Good. People are like, no, you don't need derivative. What's the buzzword in there? I mean, we saw velocity, but it said average velocity. Very good. Key word here. I know I put AVG to appreciate, but the average velocity, that's average rate of change. No calculus is needed here, right? This is a algebra 1 problem, college algebra problem. You're just like, oh, I just got to do change in y or change in x, right? F of 7 minus f of 4 over 7 minus 4. Does everyone agree? F of 7 minus f of 4 over 7 minus 4. Even though it's written like this, it means the same thing. That's all I'm going to do. F of 7 minus f of 4 all over 7 minus 4. Okay. All right, yeah, but what do you get? Well, the denominator is easy, 3. What's f of 7? 49 minus 28 plus 2. What's 51 minus 28? 23! What's f of 4? 2? Alright, what's the average velocity? 7. 7, wow, came out nice. Did they give units? Hold up. Everyone, S is measured in meters, T is in seconds. I should have written that down, I apologize. S is measured in meters. T is in seconds. So what would be our units? 7 meters per second. Not instantaneous rate of change, but that's the what? Alright. But I think you know where I'm going with this. Owen, can you find the instantaneous velocity at t equal to 4? Take a lot more work in it. I can't just do f of 7 minus f of 4. There is no 7, there's just a 4. I need this thing. With the h going to what? 0. Okay? And when I'm all said and done, everyone, I'm going to get this thing all simplified. I'm going to find this limit. I'm going to plug in what value for t? 4. Someone got me? That's it. I'm going to do this. That's my formula. This is the, we derived this. Everyone, we derived this formula. All I got to do is this. But when I'm said and done, I find this limit expression, I'm going to plug in t equals 4. And I'll find the instantaneous velocity. So you ready? Bear with me on this one. Here we go. LIM, H arrow 0. Let's start with the easy part. What little letter's down here?
H.
H. The other easy part. This just says f of x, right? So what's the f of x? It's right here, it's just a what? T squared minus 4t plus a 2, huh? But don't I have to do something with that minus here, Joe? What do you think? I have to put a what around it. Yeah, there you go. This is the only part that might bug some students. Have you done this before, pre-calculus, college algebra, or something like that? You gotta tell me what the heck is, there's S of t. What is S of t plus h? I have to write that there. So all I do is I rewrite this, but I substitute what for every t? A t plus h. So, and I think I've got enough room, right? Here I go. That would be a t plus h squared. What would this be? Minus 4 times t plus h. And this would be just a what? Good, I squeezed it in. I had enough room. I just want to leave enough room there. All right, we got to do a little algebra. Big deal, right? And as you see us doing this, everyone, do you really think that we're going to do every problem this year this way? Brilliant. You're all smart. You're like, there's got to be a quicker way to do this. You know, that's how math does, right? It's like with those with the Horace things.
Yeah.
You start eventually going, wait a minute, we only got to look at this. So I think we should just let everyone know about that when we leave today. Right? You'll feel a little relieved. You go, okay, we'll do it the long way now. If you're curious, I know your question. The answer is, you only got to do it one time the long way on the test, and after that, you never have to do it again. Because
Yeah, no, I know
You
that. I
understand
was
this?
thinking, so
I
what are
have
we
to
gonna-
assess.
No, I was really thinking, so what are we gonna say when we get out of here? Our teacher taught us to spot the Horace.
Yeah, there you go. That'll work. That was good. Hey, everyone, is that just t squared plus h squared? We gotta FOIL that. What is that?
T squared plus 2th plus h squared.
Good job, everyone. T squared plus 2th plus h squared. Is everyone okay with that? He just FOILed that. I just want to look around. Anybody, everyone all right with that? He FOILed that. He did a t plus h. Okay, now what's that? And I know everyone, I actually agree with you. You're like, gosh, this is tedious. Okay, we'll keep going. It's 2 minus t squared plus a, or t minus a, 2, all over just a little what? But expect things to cancel. In fact, expect anything that doesn't have an h attached to it to go away in the numerator. Expect that. Expect anything that doesn't have an h attached to it in the numerator to go away. Does that have an h? No? Does it go away? Yep, look. Oh, that has an h. That has an h. Does that have an h? That should go, look. That has an h. Does that have an h? Should go away. Expect that. Expect that. Hey, some students do this, look. They scratch out, they scratch out. Now what does all this become? Okay, keep writing, lim h goes to 0. Here I go, lim h goes to 0. What's this now?
2th.
2th plus h squared minus 4h. Is that it? All over h, right? Now I need to be able to simplify that because I'm still getting 0 over 0. Indeterminate form. Remember what indeterminate form? That means we can somehow manipulate this. Factor, yeah, between conjugates and all that stuff we did yesterday, we're going to factor, aren't we? What can you factor out of that whole top? H, and it'll cancel out this. Here we go. Take out, I still got to write lim h goes to 0. I want to factor out an h on top. 2t plus h minus 4 all over h. Now what do you get? Man, a lot of work just to get an instantaneous velocity. Here we go. 2t plus h minus 4. Now I'm happy, but don't leave it like this. You did all this hard work. Find the limit as h approaches 0. Now substitute h equals 0. Stick a 0 for h. What do you get for the answer? 2t minus 4. Now we're going to make a note. This is not the final answer to this question, but you're a step away. This represents instantaneous velocity at any time t. This is instantaneous velocities. Instantaneous velocity at any time t. Any time t. Right there. You wanna find the instantaneous velocity of this particle at time equal to 100 seconds? Just plug in 100 there, right? How about at 0 seconds? Plug in a 0, because it's set for t greater than or equal to 0. Hey, by the way, what's the instantaneous velocity at 0, t equal to 0? 2 times 0 minus 1, -4. But what's the answer to our question? What's the instantaneous velocity at t equal to 4? 2 times 4 minus 4 gives us 4. And what's the units?
So we can't take the derivative of the function on the test, so we have to do it one.
I got you, so you do know shortcuts.
Yeah.
Yeah, but here's the deal, you only have to do it once, and then from there on out, you can use your shortcuts. Does that sound good? You'll show it once. I don't get into like, is you gonna throw like a crazy radical at us? You know, because you could spend like 2 weeks on that one section. Because it's not easy to deal with radicals in this kind of step. Or can you all think about this? What if that was to the 5th power? You'd have to expand that,
Yeah, it'd just be bigger, but that's it.
you know? And it would be huge, wouldn't it?
Yeah.
Do you agree?
Yeah, it's not that big of a deal though.
Yeah.
It'd just be long.
Oh, it'd be long, he's right. He goes, it wouldn't be a big deal, but he goes, you spend a long time expanding that thing. Do you know Pascal's triangle? It makes it a little bit easier.
Yeah, I've heard of it.
Yeah, Pascal's triangle makes it a little easier, but it's still what?
It's massive.
Yeah, it's massive. Like just t plus h to the 5th would go from there all the way over here, expand. And you'd have to expand it. It's the only way we can get the thing going. Cool?
Alright, so show us the easy way.
Oh, hey, before we do, let's take this. So this represented the what? The instantaneous velocity? What's another word for this? This is called the what? This is the derivative. What's it the derivative of? Of s of t. So and I just want to make some other notation. This is equal to s of t, but what am I going to put right here?
S prime.
A little s prime. This is what this is. And it's huge, it's very big. This is the derivative of s with respect to t. Right? S prime at t. It represents instantaneous velocity. But before we do the shortcut, what else did this represent? I need you to go here. There's always 2 things that it talks about. I want to talk about a graph. It's instantaneous velocity, instantaneous rate of change. What else is it then?
Tangent.
It's the slope of a slope, the slope of a tangent. So could we do something right now? How about let's graph this?
No.
And then that's fine. No, it won't be hard. We're going to find the equation of the tangent line to the curve at t equal to, what was this value? 4. Does that sound good? Awesome.
I'm just thinking though, like, you know, we did the f of b minus f of a thing the other day.
Yeah.
Why couldn't you just done that? Because you know, we did like the squiggly equal.
I got you.
You know what I'm saying?
I'm with you. It's like, hey, he's like, I like how he thinks. He goes, you know, last time we just kind of did f of b minus f of a, b minus a, and then we knew to just get what? Use like 4 and 4 point what?
Oh.
01. He goes, and then you could see what's going on there. Use 4 and 4.0001, and you're going to be able to estimate, and you would get what answer. You would know it would come out to be about what? 4. I love it. But here's the deal. Here's where we're going to appreciate this. And then give it short. Well, what about if it's a little bit more complicated than that? You know what I mean? What if this thing is vicious? And it comes when you got to keep what? Plugging stuff in there and do something like that. Or what if it doesn't even just ask for it at a certain value, just come up with the expression? Then we're stuck, right? But always think like you just did, because that's right. That's good for you to go, hey, I got another one to get this, you know? I know I used the definition, but I can approximate what it is. And that's good, because that's the foundation, Joe. So that's good that you did it that way. Everyone, can I use this side right here? All right, get this out of the way. Same function, everyone. In fact, you know what, I'm going to use f of x, because we're used to y's and x's, right? There you go. F of x is equal to, what was that function? X squared minus 4x plus 2. Does anybody know what this graph looks like? It's a parabola, right? In fact, I should make a little picture of this. Can you help me graph this? Some of you are like, can I use a graphing calculator? Sure you could if you want. But does anybody know where the vertex is? Negative b over, yeah, negative b over 2a. So I got to do negative b over 2a to find the vertex. So where's the vertex of this parabola? Negative b over 2 times 1. So when the vertex is at 2, and what's 2 squared minus 4 times 2 plus 2? 6 minus 8, is that negative 2? Okay, so it's right here. there. Hey, what's going on? Can someone just figure this out for me just to get another point? What's going on with this function at x equal to 1? That's 3 minus 4. Negative 1. Alright, here you go. It's going like this. That's the bottom part. Now what's it going to do over here? It's going to go back up. Can we just get 2 more points? What's going on at t equal to 3? Or x equal to 3? So I know this, these are some points on this graph. That's the vertex. At 1 it was at negative 1. I know at 0 it got up to 2. At 3 it gets to 9 plus 2 is 11. What's 11 minus 12? It gets back to a negative 1. And I'm almost there because I want to see what's going on at 4, right? What's the function value at 4? What's going on at 4? 16 minus 16 plus a 2, what do you get? 2. Alright? So 1, 2, 1, 2, 3, 4. There's my parabola. But hey, as I did all that, some of you just pull out your what? You're like, can I just do this thing? I'm like, yeah, sure. Can we do it right? Let's just look. Quick. Clear. Straighten that out. Y equals x squared minus 4x plus 2. Zoom 6, right? Zoom 6 is a standard window. Did we make the graph correctly? Perfect. Alright, here's my question though. We'll go through all the motions. We'll even check it with the calculator. Does that sound good? We're going to check this with the calculator. We made the graph right. And I'm writing the directions up here. I want you to help me find the equation of the tangent line to this curve at the value x equal to 4. Alright? Because that's what it asked right here. So let me write all that out. And find the equation of the tangent line. So when we hear this word tangent line, everyone, how do you find slope of a tangent line? It's the what? Derivative. Everyone agree? Slope of tangent line to a curve is derivative. Slope of tangent line to a curve is derivative. Well, find the equation of the tangent line drawn to this curve above. What's this curve? F of x equal to x squared minus 4x plus 2. And at what value do you have to do this? What value do you have to find this at? At x equal to 4. So right there, by the way, what does the tangent line look like? It's not a secant, so it skims the curve in exactly what? 1 point. Very good. So our answer should look like that. Do you agree? Right? Even everyone, if you couldn't find this answer on a test, would you at least take your pencil and draw a picture and go, it's right here? I could give at least some partial credit, right? I go, well, they know what a tangent line looks like. True? True? All right. Who knows the equation of just like a straight line? Tangent lines are straight lines. Back in our...
Y equals mx plus b.
I love it. But I want another one too. That was good. That's point. That's slope-intercept form.
y minus y1 equals mx minus x1.
This is the one I want. Now I want to tell you why I want, because we got a point and a slope. I want this one. I want point slope form. So I'm going to use point slope form of a linear equation because I've got a point and I know a slope.
Yep.
You go, what's the slope formula? Oh, it's right there. We figured it out. There's no reason you and I have to do this twice. Do you agree? It's the same function. I did that on purpose. I did that on purpose. By the way, I do the same thing on a test because I want to save you time. But we did all that work and when I used the same function. So this should represent the slope of the what?
The point.
Hey, be careful. Sometimes students mistakenly think they go, is this the equation of the tangent line to the curve? Let me be specific. This is not the equation of the tangent line. This is the slope, right? This represents the slope, the steepness of that tangent line at that value, okay? But we're saying the equation of a tangent line looks like what? Let me write it out again. Y minus y sub 1 equals m times x minus x sub 1. Okay? But let me go above. I don't need all that work right there. x minus, what's the x of 1 value? Everyone, students get stuck here all the time. All the time they get stuck here. How do I figure that out? How do I get the y sub 1 associated with the x sub 1?
Just look at the.
Plug it in up there. I want to point that out, right? Notice they didn't give it to us? So let's go up here. What is it? At x equal to 4, what's the y sub 1? 16 minus 16 plus 2 is 2. It's right there, and you go, I can see it. Yep. So I just want to point that out. Sometimes students forget. Like, how do you get the y sub 1? If they only give you the x sub 1, you got to plug it in the original function. So this problem is easy. Yeah, except for one thing. Just be careful on this on the test. I need the what? M is slope, so I'll write it up here. M equals slope. But M, we now know, is slope of tangent line. It equals f prime of x, doesn't it? True? What was the slope derivative? What was it? What was the formula? I'm going to write it again. M is equal to, we don't have to duplicate this. There it is. Slope of tangent line to a curve. 2 times t minus 4. Well, now I change it to an x. That's slope. But everyone, I'm not doing 2x minus 4 here. At what x value am I evaluating the slope?
4.
Right? I'm evaluating that slope at x equal to 4. So watch what I'm going to write. I'm going to say f prime of 4 equals 2 times 4 minus 4, which is still equal to that same value over there, which was a what? 4.
So then just toss in the 4 for this one.
That's it. Now on a test, of course you can leave your answer like this. You go, I don't even have to solve for y? No, but I would. I would solve for y, I'll tell you why.
You want to use the same formula as that one.
Okay, so this represents instantaneous velocity, instantaneous rate of change of that function, but it also represents the slope of a tangent drawn to the curve. Right? And so like, that's the key. We go, this was not the equation of the tangent line, this was the slope of that tangent line.
Any tangent?
Yeah, of any tangent drawn to this curve at any point. Cool? Like you could have drawn the tangent right here. Like for instance, what would the tangent look like right there? I'm going to draw it. It would do what? It would just go like this, wouldn't it? True? What's the steepness here? Use this. Watch, I'm going to pick a point. Tell me that I'm going to do this. This will make you make the connection. What's that slope look like right there? What's that slope look like?
Zero.
The slope is 0. So can we check that? What was that x value? 2. Plug in a 2 into this equation. What's 2 times 2 minus 4? 0. Very good. Now, I'm going to try another point. How about over here? What if I drew a tangent right there? These are tangents. The slope would be positive or negative. Can you tell from the picture? Slope should be negative. True. Well, let's see. What's the x value right there? 0. What's 2 times 0 minus 4? Negative 4. So here, and feel free to put this in your notes, label this. The m right here was negative 4. What was the m over here? The m right there was 4. What's the m right there?
Oh,
Feel free to put this stuff in your notes.
I didn't actually notice that you just changed it. See?
Yeah. That's why. Oh, I'm with you. I'll be honest. So if I didn't do that,
Yeah.
I would have had, if I just changed that to a what? T squared minus 5t, I would have go through all the work again.
That's what I was.
Okay, great. Hey everyone, can you help me solve for y here? Yeah, I want to point out I use that same equation.
So,
To save some time.
going from the side, it's going to be 4 no matter what, basically, and then when the bottom is going to have to be 0. Okay.
You got it. Very good.
Duh.
Hey, what is this now?
Oh, it's
What's
going
this answer?
to y equals 4x minus 14.
So everyone, I'm gonna distribute this. 4x minus 16 plus 2 minus 14. And there it is. Now, what is this representing? The equation of which line? So let's label it. If you're going to put in your notes, which one of these 3 lines? It's this line right here with the m equals 4.
Yeah.
So in this line right here, let me just go, your y equal to 4x minus 14. Cool? Now, we definitely, that's a lot of work. On the test, you're going to want to check it with your what? Calculator, true? It shouldn't be too hard. There's got to be a button called tangent somewhere, right? Right? Alright, let's go on this thing. We already got the graph. The first thing I do want to point out, Evan, you do have to make the graph. So make sure, has everyone got their graph in there?
Yes.
Oh, I'm going to wait. Chloe, you still copying? I'll wait till you get that.
No,
up.
I'm done now.
This is pretty cool though, Chloe. What we're able to do is check this. Here we go. Did I do this right? I did a lot of work. Because sometimes people accidentally write that as their equation of the tangent. Like, no, we're gonna check this. So I got it all in there, right? There's gotta be something called a tangent. So you go, where is it? And when you see a button called draw, you gotta hit second program. It's in the middle of the calculator. There's a program button. If you hit second program, it's called draw. Which one do I want? And you have make a point. You had to draw the function first. So I'm going to number 4, right?
5.
Oh, 5, thanks. I don't want a vertical tangent. So I'm going to 5. Now I'm going to hit enter. Now, it's blanking right here. It's waiting, it's funny everyone, it's waiting for you to enter a number where you want to hit the equation. At what value did we want the equation of tangent line to occur? What x value? At x equal to 4, right? So see how nothing's happening? It's just blanking? It's waiting for you. So just hit 4, watch. 4! Nothing happened, so I gotta hit what? Enter. Now did we do it right?
Magic.
There it is, Chloe, can you see it? Look, it wrote 4x, it's a program, so someone always puts a plus here. 4x plus negative 14. 4x plus negative 14.
So how did
That
you
cool?
get to the tangent? How did you say yes?
So again, let me do this back. So first thing was, let me clear this out. Let me clear this out. What was the equation of function? X squared minus 4x plus 2, right?
Yes.
And I made the graph, I just want to see the graph. There it is. So I got that first. Now I want to get the tangent. I go to draw. And you go, where is it? Second program. You see a button called program? Second program. And look for number 5. It should say draw. And there it is. And I'm like, okay, I'll draw this. But where do you want to draw it? It's waiting. 4. And I'll hit 4 and I'll do it. Now, hey, let me pick another number. Pick another number. Come on.
8.
8. All right. Well, 8 it might not show because it's going to go off the screen. But let's see if 8 works. Is 8 on the screen here? 1, 2, 3, 4, 5. It should work.
10 by 10.
Yeah, it's a 10 by 10 winner. It's going to work. If we used 11, it wouldn't work. So keep that in mind. If we did, what about x equal 11? It's off the screen. There's it. 12x minus 62. And I want to see the line. It's kind of dotted.
Yeah.
Oh, it's because I got the dot mode still. Remember that? Let me get back to connected. Graph. Oh, I got to draw it again? That's messed up. Draw number 5. I'm going to do it at x equal to what?
8.
8. It's kind of slanted. Isn't that cool? So everyone, remember that. I mean, seriously, it's there for support because we really want students. There's a misconception when you go, find the equation at the tangent line, and students go, okay, here it is. And you go, no, that's the slope of the tangent line. That's the m. This is the equation. You got to put the m in there, right? Hey, so I promise you before you leave, we would do what? Do shortcuts. So how many times you're going to have to do it this way on my test? Once. And after that, all the way up until the final exam, do you ever have to do it the long way again? No. Right? But before you leave, can we just get a sense of how easy it is to find derivatives by the rotor rules? So you're not like dropping my class today because you just saw this and you're like, are we going to do this all year? So let's do it. Ready? That's it. You show it once, you go, hey, here it is. It shows me that Joe and everyone knows the definition of the derivative, and they could do it the long way if they had to. If you had to tutor someone and explain it to them, you could. But after that, you can always use the what? Shortcut. Sound good? All right. So that means we're wiping this whole thing out, aren't we? All right, here. Get out, 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 get out. Find the instantaneous, what was it?
Velocity.
All right, get this average velocity right. And this doesn't work with averages. So Joe, you brought it up. You go, man, just do that 4.01 thing, and that was brilliant. But I think you're going to like this even better. This is introduced in section everyone 3.1. Okay, but it doesn't hurt if you just show people now. You know why? Number 1, can't you use this to check your work? I mean, could you imagine doing all that work? You made one simple error, like you didn't FOIL the t plus h squared. There's your answer. So here it is. I want you to take this. Let's first write down instantaneous velocity is equal to what? S prime of t. Hey, does that mean we can call S prime of t vt? V of t? V for velocity, does that work? What do you think V prime of t is? Acceleration. You all agree? I want to read the derivative of position with respect to time is velocity. What's the change of velocity in time? Like, you're changing the velocity in your car, you're pushing the what? Accelerator. Except, so that'd be, but that's via t. Alright, start with the power here. What's the power? 2. Put it in front, and then I want you to decrease this power here by 1. It was a 2, I want you to subtract 1 from it. What's 2 minus 1? Okay. Do you have to write the 1 now? No. So this is the actual, this is called the power rule. Alright. Minus, I need you to do it again. Leave that 4 in front. What's that power right there? A 1. I need you to do it again. Multiply the 1 to the 4 in front. What's 1 times 4? 4. Now I need you to decrease this power by what? 1. What's 1 minus 1? 0. By the way, what is t to a 0 power? 1. Oh, so that goes away. Now, this last thing, everyone, I don't really want you to think about doing this whole rule because we know that derivative means slope. Does anyone know what the slope of any constant is? Look at my hand. What's the slope of any line is a constant? 0. So what happened to that 2? 0. Did we get it? Did we get the same answer? Wasn't it a little bit less work? I mean, come on now. So you follow me? Use that to your advantage to check your work, right? Let me read it. How many times you got to do it that long way? Once. You have to do it again on the final? No. Just once. It shows me, at least for me, like you have this, I have students who've been assessed on this, they appreciate, they know where it came from. It's always good to know the origin of things, you know? So you know where it came from, but then it took a lot of work to kind of get these little rules down. Joe, you okay with the whole rule?
So you take the exponent and put it in front of the t.
And then what do you do with the power afterwards? You always decrease it by how much?
1.
By 1. So let's see how good you are. Ready? Make something even higher. Go higher than t. Come on, go higher.
4.
All right, to the 4th. Now give me a t cubed. What's the coefficient?
5
All right, keep going. Joe, what's next? Minus, give us a number.
6
T squared. Other coefficient?
1
Okay, 1. T to the 1st. And what's the constant at the end?
700,000.
700. Everyone, I want you to find S prime of t. The instantaneous velocity.
14.
I want you to find the derivative. Now, could you imagine how long it would take the other way? Hey, that would take a while. You gotta admit, right?
If you
That would take forever.
if you gave me some like chocolate chip cookies and some milk,
I'm gonna give you a notebook. There you go. Right? How long would it take? But this should take us seconds. Start here, Joe. What is it? 4 where?
14.
T to the 3rd. Good.
15 t squared.
3 times 5 is 15. Notice she multiplied it. And then you decrease the power by 1 integer, 2, minus 12t. Plus, yeah, this is the one that's tricky. Everyone okay with this?
1.
You put a 1, you multiply a 1, you get a 1, but what's t to a 0? So that's why that just became a plus 1. That sometimes takes students a while to get used to. So that's plus 1, and what's the derivative constant? Now, and can you find the instantaneous velocity at t equal to 1 second? Can you find its velocity at t equal to 1 second?
4 minus 15 minus 12 plus 1.
4 plus 15 minus 12 plus 1 plus 0 is, how fast is that particle going? 8 meters per second. So it's still meters in seconds, right? Do you follow me? So please feel free to use this as a check, right? You know what I mean? Or just do it this way and then just scrabble on your test. When you write F, go, lim, t goes to 0, and just go, you know, like right where I can't even read it. And then just go, 8. You know what I mean? That's kind of writing like he won't be able to read my writing. True. Good job, everyone. Hey, if you really want to practice that definition, the other ones, I'll tell you what, this can get a little nasty with like natural logs, trig functions. Trig functions, you got to know your trig identities to make this thing get what? Simplified. You follow me? But yeah, it's like I teach Calc 3, and we always do it the short way, so I wouldn't kill you with that stuff. Have a great day. Hey, where are we meeting tomorrow? Forestano? Right? Dick, you okay with that power rule thing? We can use it to check, right?
Yeah.
Whoa.